Okay, so let's look at this one. The magnetic flux through a loop shown in the accompanying figure varies with time according to, so this is the magnetic flux, that's the functional form of the magnetic flux, where the flux is in milliwebers. Okay, Weber is the SI unit, and this is in milliweber, so thousandth of a Weber. What are the direction and magnitude of the current through the 5 ohm resistor at t equal to 0, t equal to 10 minus 2.17 times 10 minus 2 seconds, and t equal to that. All right, so let's look at so the flux is decreasing as time increases. You can see that the magnetic field is coming out of the plane of the paper, and so the magnetic field strength is decreasing since the flux is decreasing. Okay. Now Mr. Lenz says if the flux changes, the induced current is such that it wants to prevent, it works against the decrease of the flux. So and a current, so if the magnetic field strength is decreasing, the induced current should try and increase it. So a current will be induced in this direction, and you can stick your thumb out in the direction of the current, and your fingers will point. Okay, or if you stick your right hand fingers in the direction of the current, your thumb points in the direction of the induced magnetic field. Okay, so anyway, that is the direction of the, this is the direction of the current according to Lenz's law. Okay, so this current, the current in the resistor will be in that direction. Okay, so we found the direction of the current, and we have to find the magnitude of the current. Okay, so let's do. The current is the induced EMF divided by the resistance, and the induced EMF is, we are only interested in the magnitude, is dphi by dt. Okay, and let's figure out dphi by dt. The magnetic flux is 2 e to the power of minus 3t sine 120 pi t. All right, and there's a 10 minus 3 because the flux was in milliwebers, and there's the flux, and this is equal to, so point 2 times 10 minus 3 is 0.002. Okay, the derivative of this is minus 3 e to the power minus 3t sine 120 pi t plus 0.002 e to the power minus 3t. Derivative of sine is cosine, so 120 pi cosine, oops, I'm running out of space. Okay, we'll make this common. Okay, so I'm going to gain some space here. Cosine 120 pi t. Okay, there we go. All right. Now what is it that we want to find? We want to find the value of this at various times. Okay, again, what I'll do is I will do part B, or I'll find part A. Okay, part A is a little easy, hopefully. Okay, dphi by dt at t equal to 0 is 0.0. Okay, actually I'll just do a new sheet because we're going to run out of room. Okay, so here's okay, my pen is running out of battery, so let me charge it for 10 seconds and then we'll continue. Alright, let's see. Will it copy now? We want to copy. Okay, I guess I'll have to write it by hand. So dphi, and we are going to, what part did we say we're going to do? Okay, we'll do part A. dphi by dt is 0.002 minus 3 e to the power minus alpha t minus 3t sine 125 t plus e to the power cosine 120 pi t. Okay, so we are going to evaluate this at t equal to 0, and that's equal to, at t equal to 0, this is 1 and this is 0, sine of 0 is 0, so this term drops out. This is 120 pi, cosine 0 is 1. Okay, so at t equal to 0, this is equal to 120 pi, okay, and that's equal to, so this is dphi by dt. Okay, so this is equal to 0.75 Webers. Okay, no, Webers per second. Okay, this is, flux is measured in Webers and Webers per second. Okay, so what is it that we want to find? What is the magnitude and direction? We've already done the direction of the current. Okay, and the magnitude of the current. So now the current is I is EMF divided by R, and the EMF is dphi by dt. Okay. The magnitude of the current is, so it's 5 ohms, so 0.75 Webers per second divided by 5 ohms, and that's equal to 0.15 amps. Alright, that takes care of that. I will evaluate that for one more time. So what we'll do is we will evaluate this at the second time. This time essentially is infinite time, and the current will go to 0. The exponential term will kill that, and you can check that. So I'll just evaluate it at this time. It looks strange, but we'll look at it. Let's see what's going on. So part B, t equal to 0.0217 seconds. Is that right? Yep, 0.0217 seconds. So let's 0.21 millisecond, 217 milliseconds later. Okay, so let's see, can we copy this? Will it copy this time? Okay, the copy function doesn't seem to be working. Okay, so let's evaluate it at that time, at this time, and that's equal to 0.002 minus 3. Let's see, e to the power of minus 3 times 0.0217. What is the value of this? Okay, so this value is 0.94, or 0.937. Okay, so that's an aside. So it's, this value is 0.97. Okay, so let's write that down. 0.937 and sine 120 pi. To 0.0217 plus 0.937. The exponential factor is 0.937, 120 pi cosine 125 into 0.0217. Okay. Okay, again, this has to be dimensionless, so 120 pi is inverse seconds, since t is in seconds. Okay, so let's evaluate these. And so that'll come out in radians, and we'll have to convert that to degrees, or you set your calculator to radian mode. All right. So let's sine of 120 into pi into 0.0217 equal to, so that works out to minus 3 times 0.37 times 0.947 plus 0.937 times 120 pi times cosine that. Negative 0.32. All right, so there is d phi by dt, and let's calculate. So simplify this. Both terms are negative. Okay. So let's add a page below. Okay, d phi by dt works out to, let me evaluate this. Okay, 3 into 0.937 into 0.947 plus 0.937 into 100 pi into 0.32, 115.7. So d phi by dt works out to negative 0.23. Okay, so the current at that time would be, so current at seconds would be 1 over R 1 over R dV by dt. Okay, so 0.046 amps equal to, so current at T equal to 0.0217 seconds is equal to 0.046 amps or 46 milliamps. Alright, so we found the currents at the two times. Just a little algebra, a little messy algebra, but we got through it. Okay, so that covers that problem.